So today we are if you think of database as a series of units, we are tackling the last unit. So the first unit was kind of how you query an SQL database and how to set it up using the DDL. The second unit was the theoretical basis, which was relational algebra and calculus. The third unit would have been design. And the fourth unit is physical database design, which is what we'll be talking about this week and next week. Actually, Thursday is fall break, so this Tuesday and next Tuesday. And then, as you can see, we have an exam review session, and whatever we don't get to on extendable hashing, we'll cover a week from Thursday, and then 2 weeks from today we have our midterm exam. Don't worry too much about it yet. We'll talk about it more next Tuesday, but it'll just cover the database portion of the course. So, as I said, we'll be talking about physical design today, primarily about how we use indices to make accesses to the disk faster, and also characteristics of secondary storage that make it slower than random access memory or solid state memory. And then next Tuesday we'll be talking more about a couple file organizations, B trees and extendable hashing, which are extensions of binary trees and hashing respectively, adapted essentially for secondary storage. So the goal of physical design is to map the relations we have defined onto the file system. And the second goal is to select a set of indices to aid the query processor. The query processor is what parses your query and then constructs a plan for accessing the relations in the query in order to efficiently return tuples as the result. And it will take advantage of any indices that you may have placed on various attributes or sets of attributes in the relation. So we'll get to indices in a moment. Before we do that, we have to talk about some of the basic characteristics of disk. Eventually, this section will go away because increasingly secondary memory is transforming to solid state memory. Just show of hands, how many of you have laptops that use solid state memory for secondary storage? Okay, and how many still have ones that use a hard disk? Okay, it's about 2 to 1. So it's still the case that hard disks are used to store a great deal of information. It's going more towards solid state. Regardless of whether you use a hard drive or solid state memory, getting access to what we call secondary storage is slower than getting access to RAM. Okay, so we call RAM primary memory or primary storage on the level 1, level 2, level 3 caches. That's part of that. That's very fast memory, but it's also temporary. You turn off the computer and you lose it. Secondary storage refers to persistent memory. You turn off the computer, that memory persists. And so that's where we store files. And traditionally, it's been on a disk. And so let's first just talk quickly about a disk. A disk, if you have not ever seen one, and all of you are too young to have seen a record player, how many actually, I bet you still have, how many have not seen a record player? There we go, so, okay, so you've still at least seen one. So basically, a disk is what you would think. It's a round platter. And generally, you have a stack of them as part of a hard disk drive. Now, in your laptops, you have only one, but in a commercial database system, you would have a stack of them. And you'd have a spindle, like a record player, that moves back and forth with its arm, and it's able to read off of the disks. So the disks then are organized into tracks, just like the old records used to have songs that were organized on tracks. the disks have tracks. And I'm not a hardware person, so I'm not exactly sure whether you can get, it seems unlikely that you can get as much data on that inner sector as you can get on the outer sector. So my guess is they somehow get more data onto the outer sectors, but how that's done, I don't know, and it's neither here nor there for this course. Now, so the disks are divided into sectors, and then, so each of those rings, concentric rings, is a sector, or at least that's how I learned. And then each sector is divided into blocks, which are the unit that you actually read into main memory. So when you access a file, like when you read a line from a file, it doesn't actually just bring that one line in for the file. It actually brings in an entire block that contains that file. And if the next line to be read is in that block is cached, the file system actually doesn't have to go back out to the disk. It actually is able to read it from that cached block. Okay? So the unit of memory that comes in with each so-called secondary memory access or disk access is a block. In Unix, that block is usually 4096 bytes. But different operating systems can define a different number of bytes for a block. So in a disk, there's kind of two elements for the access times that control access times. First, there is the seek time. So that is the time for the spindle to reach the appropriate track. Okay, I called it a sector, but they're also called tracks, those concentric rings I drew. So it takes some amount of time for the spindle, the read-write heads, to reach the appropriate track. Okay, they move back and forth mechanically, so that's called seek time. Then once it's at the appropriate track, the appropriate block has to rotate under the read-write head, because just because you're on the right track doesn't mean the block is under the read-write head. It may have to rotate under the read-write head. That's called rotational latency. So the time it takes for the appropriate sector block to rotate under the read-write arm. So the seek and rotational latency times have really flatlined. And the times, this is from 2017. Before class, I quickly checked, and they really haven't changed in the last year, and they actually have not really changed for the last 5 years. So for commercial grade high-end disks, seek times are roughly 3 to 4 milliseconds. For your average desktop, it's 9 milliseconds, and for your mobile devices like your laptop, it's about 12 milliseconds, 12 to 15 milliseconds. And then your rotational latency is anywhere from 2 to 7 milliseconds. So rotational latency is on average half. You're going to take whatever is half of that. So it's probably usually about 1 to 3.5 milliseconds to get to the right block. So once you're at the right block and you start reading it, now we care about something called the transfer rate, which is how fast it can move what it's reading into memory. So for commercial disks, it's about 200 to 300 megabytes per second that they can both read and write. For a consumer, it's about 200 megabytes, so on the low end of the enterprise grade. And that is not as fast typically as you could read out of main memory, but that's neither here nor there. So they're being replaced by solid state devices, hard disks are, and right now they're about 4 times as expensive as hard disk drives. So if you just look at this cost, last year the cost per gigabyte for solid state was about 24 cents, and for a hard disk drive it was about $1. So you still pay premium price for solid state memory, but it's worth every penny in my opinion, because everything comes up faster. So with solid state, you have next to no seek time. The seek time is effectively, or rotational latency. Obviously, there's no mechanical parts. So it's just basically going out to the right solid state element, sending an electrical signal to it, and locating it. So it's less than 1 millisecond to find the appropriate part of solid state memory. So that's much less than for a disk. And then they transfer anywhere from 200 megabits per second to 2.5 gigabytes per second. In other words, solid state memory can be 10 times faster than a disk on its transfer rates. Now, they have one significant drawback in your devices, which is that having fast write on solid state memories is expensive. And so usually for consumer devices like our laptops, you have slow writes to your solid state memory. You have fast read but slow write. And that's what that says up there. The write times for less expensive read your laptop SSD 10 times slower than the read rate. So you may have only 20 to 250 megabytes of write speed. Okay, and for high-end SSDs, the kind that Google or Amazon uses, the write times are comparable to the read times, but of course they pay more for them. No matter what happens, even when disks, hard drives get replaced by solid state, it is still going to be a bit of an issue to access things in secondary memory because it's still slower than primary memory. So we're still going to be concerned with trying to minimize the number of reads and writes that we make to secondary memory. So the whole goal of the query optimizer, so I guess when we talk about physical design and the mapping of relations to files, what we're trying to do is help the query optimizer minimize the cost of minimize the number of reads and writes it has to make. We're willing to give up a bunch of CPU processing time to minimize the cost of a read or write because you can typically execute on the order of some number of either hundreds of thousands or millions of instructions per read. So you can do a lot of processing in the time it takes to do a single read or write, at least on a disk. You don't get as many instructions on solid state. Okay, so just the takeaway message here is secondary memory slower than primary memory, and we're going to want to minimize the numbers of reads and writes to it. So we have two basic decisions to make as a database designer when we map our relations to files. First of all, we have to choose a file organization for each of our relations, and we'll choose one of three types typically. A heap, which is not a binary heap. It is simply a unordered file. The kind that you probably have dealt with, like input files, are heaps. B+ trees, which are extensions of binary search trees, and extendable hashes, which are extensions of hashing. Basically, you use a B+ tree for what we call the clustering index, and we use extendable hashing for all of the so-called secondary indices, which we'll define those terms now. So the second thing we need to do after we've chosen our file organization is to choose indices that will assist the query optimizer. So an index is a file organized on either a single attribute or some set of attributes, and that has pointers to the corresponding records on the file system. Remember, I said once we got down to the file system level, we'd no longer refer to a relation, we would say a file. We'd no longer say a tuple, we would say a record. And we would no longer say an attribute, we will say field. So get used to me kind of now talking about files, records, and fields rather than relations, tuples, and attributes. But I'll be interchanging. At any rate, an index is basically sitting there, and let's say it's an index on last name. So it might be something like Al, Betty, and it's going to have some physical disk address that's pointing out to our disks. And so these are the disk. And this is obviously a conceptual rendering of the disk, not the one that I just did. But they have physical memory addresses that are pointing to the individual records on the disk. So if I chose a heap, or let's say I didn't even have an index on name, and I wanted to find Betty, without the index, my only hope is to do what? What's my only hope if I have no index on name and I want to find the record associated with Betty? Just traverse the entire file out on secondary memory, which means I have to read potentially every single block of that file. Whereas if I have an index, then I can hopefully quickly find Betty in the index, and that will give me an address on the disk, and that will require only one disk access. So an index can help speed up the process of finding records on the disk. Okay, so there's three types of indices. One is called a primary index, and that means the file is physically clustered on the primary key. That means sorted. When I say clustered, I mean sorted. Clustered, sorted, clustered, sorted, sorted, clustered. Same thing. Okay, so it's sorted by the primary key. It is very rare to actually sort or cluster on the primary key. And the reason is that primary keys are artificial. They have no real meaning. Okay? So usually when we choose to cluster on an attribute, what we want, is to be able to efficiently perform what is called a range query. Okay, so there's two types of queries. There are range queries and point queries. Okay, a range query So a range query returns all records in a range, okay, such as all records with salaries between 10K and 40K. A point query returns all records with a specific value. So basically a point query is using equality. Okay, so a point query is basically an equality comparison. A range query is an inequality comparison, or in SQL, between. Okay, where you say where salary between 10K and 40K. So that's a range query. So we typically choose to put a cluster index on an attribute or set of attributes that are likely to be involved in a range query. Things like last name, salary. I used to be a runner, so race times. You might want, for example, all runners who finished a race between 15 and 17 minutes. I used to love that query because I wanted to know who my competitors were. Okay? So those are range queries. You tend to put the cluster index on that type of attribute. That tends not to be the primary key, because the primary key being artificial, you almost never do a range query on a primary key. So the cluster index, both a primary and a cluster index, is a clustering index. There's only one cluster or primary index per file. You can only cluster on one set of attributes. Okay, so there's only one of those per file. The remaining indices are secondary indices. So they're used to index on non-clustered attributes. And it turns out extendable hashing is almost always used for secondary indices, and B+ trees are almost always used for cluster indices, because B+ trees, it turns out, physically cluster things together, and hashing works precisely because it actually randomizes everything. So secondary indices tend to be extendable hashing. Cluster indices tend to be B+ trees. Okay? And in addition to just helping the query optimizer efficiently find records on the disk, some queries, especially aggregate queries, you can answer by looking only at the index. For example, if I have an index on salary and I ask for the minimum salary, I don't even have to go out to the file to find the minimum salary. I can find the minimum salary from the index. So a query optimizer, being smart, would actually do select min salary from foo by querying only the secondary index on the salary. So the next thing then, so I just pretty much told you the design decision for mapping relations to files. Basically, the clustered index will be a B+. So most files are organized as B+ trees. And then most secondary indices are organized as extendable hashes. We'll see that there's a few very small relations that are stored as heaps. Okay, and we'll talk about that a little later. But first we'll just talk about things to consider when choosing indices. So there's things, attributes you should index and attributes you tend not to index. So you almost always index the primary key if it's not the cluster index, because you're always doing joins on primary keys. Same thing with foreign keys. Foreign keys and primary keys are always being joined. So you're often looking for information like, what is the, find the properties managed by Brad van der Zanden. Well, that means you're going to be joining, you're going to find the staff record with Brad van der Zanden. You're going to pull the staff number, which is a primary key, and you're going to join that with the properties relation, which has staff number as a foreign key. Well, once you know Brad van der Zanden, you have my staff number. So it's going to be a lot more efficient to perform the join if you can, in the property relation, just look up the staff numbers that are mine, rather than searching the entire property number, or sorry, the entire property relation. So you tend to put indices on your all primary keys and all foreign keys because they're used so frequently in joins. The third one is the squishiest. So we tend to add secondary indices to any attribute heavily used in selection queries. That's more of a judgment call, something you make when you're designing the database, and then once it goes into production, you often keep statistics about queries, and you can fine-tune it once it goes into production, because then you have a much better idea as to what are actually the heavily used attributes. Then you tend to add secondary indices for any attribute frequently used in sorting. So any query that any attribute that's going to be frequently ordered by or grouped by or involved in things like union or distinct operations. Okay, it's a lot faster if you can, for example, if I do an aggregate operation using group by, it's a lot easier if the records have already been grouped for me in a secondary index. Then 5 and 6 are essentially the same, which is indices that, or I'm sorry, attributes involved in aggregate functions, because you can almost always use an index-only plan for aggregate functions. If those attributes have been indexed, typically you only have to go to the index in order to solve them. 6 is a little more general because it's potentially the case that you could have other attributes that result in index-only plans. For example, if You just don't really get it though. I guess the most common would be if you had a subset of attributes. So in the hotel relation, you might often want to know about all index-only plans. Having trouble coming up with it outside of aggregates. But suffice it to say, any query that could be solved with just consulting the index, you might consider indexing those attributes. An important thing in all of this is sometimes you put an attribute on multiple indices. I'm sorry, multiple attributes. So in the hotel relation, you had, not the hotel relation, in the room relation, you had room number, hotel number, you had type, you had price. Those were the big ones. So here you might put an index on both the room number and the hotel number, meaning the index is actually on this both of those attributes. So an important thing is a index does not have to be on a single attribute. You can put it on multiple attributes, particularly when those multiple attributes all comprise the primary key. Okay. Another example is, you may remember we had the functional dependency that a branch number and a position determined a salary. So if it turned out that this was a common query, that you wanted to find the salary associated with a particular position, you would probably actually have to create a secondary index on both of those attributes, because the position alone does not determine the salary. It also depends on the branch number. So in this case, if the query was often executed, you would put the secondary index would be on both branch number and position. So both attributes would be in that secondary index. So is that clear that you don't always index single attributes? Sometimes it's a combination of attributes that get indexed. And when you do that, you would tend to choose one of the attributes as the primary key, and the remaining attributes would be secondary key. So this secondary index probably would, either way would work. You might decide to make the primary key branch number, primary sort branch number, and the secondary sort position, or vice versa. Questions about that? This is black art, okay? It is something you get a lot better at if you do it a lot in practice. I actually have not had to do it because the relations I deal with are so small, this doesn't really matter. But in a real system like at Google or Amazon, it's crucial. So then things not to index, and this is where we talk about small relations. So small relations, it's meaningless or actually inefficient to index them. Think of the branch relation for our property management firm. How many blocks, if the block is 4,096 bytes, and we have, say, 20 branches, which is a fairly good-sized company, how many blocks do you think the branch relation takes in secondary memory? 20 branches, 4,000 bytes. Roughly speaking, I mean, just make a reasonable estimate at the size of a tuple. You really think it's going to be more than 200 bytes? No. So 20 times 200 is 4,000. It's very likely that the entire branch relation fits in one memory block. Why would we index that? Okay, if we indexed it, we would have an extra memory block for the index, Then we'd have the block for the relation. So every access would require two block accesses, one to the index, and every entry in the index would point to the same block, and then we'd go and we'd read in that block. So we just managed to go from needing one read to two reads. That doesn't really help us, okay? The same thing goes for like two block relations. You probably, if we up the ante to 100 branches, we still might not index it if it occupies two blocks. And why is that? Well, we're going to read two blocks potentially to find a branch. If we have an index on it, we have to read the block from the index and then the block from the file. That's guaranteed two block accesses, right? Still no win. So generally, relations that have two or fewer blocks, there's absolutely no reason to index them. Once we're up to 3 blocks, now we start to consider indexing them because now it could be a win. So I'm just going to put here if I can find my handy dandy marker, something that says generally if the relation is less than, so small relations, okay, which are less than or equal to 2 blocks. So generally, relations that are 2 blocks or less, you would not be indexing for sure. Okay, second one, an attribute or relation that is frequently updated. Does anyone can think of a reason why if an attribute or is being frequently updated, we might not want to index it? Yep, because it changes the index as well. So not only are you modifying the record in the file, you also have to modify the index. So every modification is now at least 2 writes rather than 1. And you have to find it in 2 places rather than 1. So you may be reluctant to index frequently updated attributes. But so for example, you almost never update the primary key. Okay? Not once since I've been at UT have they changed my personnel number. That may be wrong. They may have changed it. They may have gone to a different system, but they never just said, hey, here's a different number. No one has given me a different social security number since I was born. Okay, so primary keys, foreign keys don't tend to get updated a lot. Things like salary don't get updated a lot. I wish I got a 5% increase every day, but I don't. Okay, I'd be the richest man in the world very quickly. So there are a lot of attributes that don't get updated frequently. There are others that do. If you're Amazon, you sure hope that your quantity fields are updated very frequently, right? I mean, you're hoping to move inventory. You're hoping it goes down, 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 down with an occasional bump when you get new inventory in stock. So quantity would probably not be a good field to index because it's going to be updated so frequently. Also, quite frankly, you rarely do a query on the quantity. You don't say where quantity equals 10 or where quantity between 10 and 40. I suppose you might run a query that says where quantity less than 10 because you may need to restock. But nonetheless, in that case, you're probably just going to run through the entire database. Okay, because that brings us to 3. There's no reason to index an attribute if queries involving it are likely to retrieve a significant proportion of the relation. And this one's a funny one. So let's say that you expect a query to, on average, return only 1 record per block. And let's say that there are 200 records. Let's say there's 400 records per block. Okay? 400 records per block. And you expect only 1 record per block to be returned. You're thinking, surely that is, not bad. I mean, only 1/4 of 1% of the file is being returned. It's horrible. It likely means that every single block in your file has to be read, though. Okay, because the expected value of that query is still 1 record per block, you're probably going to end up reading just about every single block in the file anyhow, so the index is a waste of time. So only if the expected number of records per block is way less than 1 are you going to put an index on it. And that goes back to quantity. Okay, so not only is quantity frequently updated, but when I'm running my restock report, there's a good chance that every day, if I'm Amazon or eBay or some other company, that I'm running low on inventory on a whole bunch of products. So it's likely that when I say give me all records whose quantity is less than 10, while it may not return a significant percentage of the database, it's likely that the expected number of records per block is going to be up there around 1, making quantity also a bad bet for indexing by this third one. Okay? So range queries would be things that are often involved in range queries tend to also, well, they tend to be good for clustering, but things that are point queries tend to be good for indexing because they don't come in very much. Queries on attributes that are being involved in range queries, you have to be a little more careful about whether you're going to index them or not, because then the expected number of records per block may be up there around 1. Especially like quantity, where we're not indexing, we're not sorting it. Okay, the final thing is long character strings. Okay, if it's addresses, we don't tend to index on street addresses. They're long. We don't tend to write queries on them to begin with, but sometimes I know we do, like we say, where street address equals 1678 Cardiff Road. But frequently, it's infrequent to do an access on a street address, and they are long character strings. Anyone know why long character strings is bad for an index? You have to store the index. Bingo. So let's say that we have a directory relation that gives information about staff. The record takes 60 bytes and the street address takes 40 bytes. If you index the street address, you're essentially storing the relation twice, once in the index and once in the file. So anytime you have attributes that are long character strings, you're probably essentially restoring the file a second time when you index on that attribute. That's bad, okay, because that's a lot of storage often. So that's a performance versus storage trade-off. Obviously, for the queries where I have to search the street address, I'm going to have to look through every record in the file, but at least I'm not wasting, a big chunk of my file system indexing on it. Now, these things obviously can conflict with one another. What is a long character string that you think is going to be frequently queried, and hence we're probably going to have to index whether we like it or not? What's another character string that's a very frequent query? Name. Okay, you probably can't get away with, while you probably won't put an index on first name, you probably can't avoid putting an index on last name. It's just too frequently queried. So even though last names can result in long character strings, you tend to end up indexing them anyhow because they're so frequently used. So that's why I said it's black art. It's not like it's an algorithm, because there are things in part A that say, yes, I should index the name attribute. And then you'll find things in B, things not to index, and you say, why, it's a long character string, I probably shouldn't index it. So then it's a balancing act. You just have to use judgment. The more you've done it, the better your judgment is. In the beginning, you make some assumptions about your queries, and Based on the assumptions about how frequently various queries will be executed, you choose your indices. Then you monitor the performance of your database. You log the queries. There will be queries you didn't expect. The frequencies will vary from what you expected. So based on what you see, you'll update the indices. So it's an evolving process. As a database administrator, you don't just do it once and leave it for all time. You're constantly fine-tuning, or at the beginning at least, you're constantly fine-tuning. Okay? So questions about that? You'll get to do this on the homework, and basically when you do it on the homework, what you want to do is go to my physical design notes, and you'll be asked you'll be given some relations, you'll be given some sample queries, or you may not be actually, but you won't be given queries. You'll be asked to make some assumptions about what you think would be common queries, and based on that, you'll be asked to decide whether you'll put indices on certain attributes or not, and I'll expect you to explain your rationale in terms of these factors. Okay, so that's homework 5. Then the book goes into analyzing transactions. What a headache. In advance, you have pretty much no idea what the frequency of the transactions are going to be. You just have to guess. And basically, you look at the few that will be frequently executed and go from there. The book had a long section on it, which I distilled down to that one sentence. Okay, it's black art. Okay, we good with indices? And we never went over the DDL for them, but in the SQL DDL and in the MySQL DDL, there is a way to specify that you want to put an index on it. In fact, let me go back in my notes, way back to the DDL slides. And now I'll go to the very end. And at the very end, before I had views, come on. There we go. Nope. Still views. I didn't realize how many notes there. So there's the syntax. Create index, index name on table name, some number of columns in parentheses. You say whether they're ascending or descending. If it happens to be a cluster index, if it's not a cluster index, there's no need to do it. But generally, you would be, if you're doing any kind of range query using the index, you would specify ascending or descending. If it's primarily a point query, like last names, then you wouldn't have ascending or descending because you're not really doing it you're not using a range query. You want to allow it to use extendable hashing. As soon as you say ascending or descending, you've essentially chosen a B+ tree. So if you put everything in sorted order, you have chosen a B+ tree. You've excluded extendable hashing. Hashing is faster than B+ trees. So in general, you don't want to force it to put it in sorted order unless it's critical, meaning you're going to do range queries. Okay? I can't repeat it too often. If you only put in sorted order if you plan to do range queries on the attribute a lot. Point queries, you don't sort them. Okay? So here's just some example. Create index, staff number index on staff relation and the name of the attribute. Here's one on 2 attributes. Okay, pretty easy. And you can do drop indices as well. Yes?
So that says the default order is ascending, so does that mean like it defaults to B+ tree?
Yeah, I saw that too. It does seem to suggest that that would default to a B+ tree. So I have to go actually and look at that. Because there's got to be a way to, unless Yeah, there's just got to be a way, because if it's assuming it's ascending order, it's going to use a B plus tree. So I'm going to go look at that. That's the first time I ever really looked closely at the index stuff. So I'll check it out. Okay. So from there, we move to the two kinds of data structures that we typically use for organizing our indices, and those are B plus trees and extendable hashing. If you're in Dr. Plank's 494 course, have you done his amazing B plus tree lab yet? Working on it right now. So if you're in that course, you've already seen B plus trees, but if you're not in the course, you haven't seen B plus trees, so you still have to do it. Also, are you doing B plus trees or straight B trees? So B plus, okay, so B plus tree, let me quickly say it. B plus tree is where you don't store the values in the interior nodes. You store keys only in the interior nodes, and only at the leaves do you store. Okay, you're doing B plus trees. Okay. But at any rate, many of you aren't taking Dr. Plank's course, so we still need to go over it, and I don't think any of you are going over extendable hashing. So, are you serious? I've never heard of a B minus tree.
He probably said that because we're not doing deletion. We're only doing like insertion.
Okay, I gotcha. So it's not as much. They're taking away stuff. Okay. So I've given you actually some notes for doing that. So actually I'm going to go to those notes now. Actually, before we do that, the obvious question is, why can't we just go with a binary search tree? Binary search trees work great in main memory. Why are you going to torture us by making us learn a new type of tree? So let's take a look at this. Let's say we did use a binary tree. Let's say that we were doing it on salary. So maybe it's 50K, this one is 25K, this one is maybe 75K, 100K, this might be 80K, so on and so forth. And we all know that it gets to a depth of log 2 of n. Right? So let's say that we have an organization that has 10,000 employees. So it means it gets to a depth of 10,000, which is 2 to the, let's see, 4,096 I think is 2 to the 12th. So it's roughly 2 to the 14. So I think this is roughly 14. Does anyone know what might be bad about that number in the context of secondary storage? Like, that might be the number of block reads we have. Okay, that's not good. Basically, every block would consist of only 2 children. So first of all, our blocks would be hugely vacant. Our blocks would have almost nothing in them. So we'd be wasting enormous amounts of space. If we had 4,096 bytes, and our salaries took up 4 bytes, and the memory addresses, the physical addresses took up another 8 bytes, we'd be storing a whopping like 24 bytes, maybe 30 bytes per block. So our blocks would be 99% empty, and we would be having to read roughly 14 of them before we got down to the leaf. That's too many blocks. We don't want to be reading 14 blocks. We want to be reading more like 2 or 3. And in addition to that, we would like our blocks to be almost 100% full, not 99% empty. because that's a lot more disk space that we have to buy, or a lot more solid state memory, and we don't really want to waste money on empty storage now, do we? So the problem with binary search trees is their branching factors are too low for secondary memory. What we want to do is pump up the branching factor so that effectively every block has just about is 100% full. That is, as many children as we can cram into one block is what we want to do, because the average level of a tree with m children, if we have m children, then the number of levels goes down to order log m. So the bigger m, the smaller order log m. Okay? So if we do, say we could cram 100 salaries into our things, log 100 of 10,000 is what? 2. That's a lot fewer block accesses to get to our salaries. So that was the idea behind B trees and later B plus trees, is that you would just go to a much bigger branching factor. So you could have many more children than just the binary case. The drawback is that now, in order to find something, so let's now actually look at a binary tree. So you see under course materials, I have something for B plus trees because I'm not a big fan of the book. That's no good. Okay, let's go for my file. Easy, just to hang on for a moment while I find my notes. And there we go, now we get the whole file. Okay, so a B plus tree, that's what it looks like. Okay, it's got a lot of branching out. The disadvantage is when you're trying to figure out which child to follow, you may have to do a linear search through every node that's a child, right? So if let's go to here. So now if we have 50K, and down here we have 10K, 30K, I'll say, again, 60K, 80K, 100K. Now, let's say that I'm looking for someone with a 90K salary. I have to search through all of this to get to this spot right there. So there's more things to search. It's more like a linear search effectively. Or if it's ordered, you can do a binary search on it. But still, it's not as fast as a binary search tree. So B trees in main memory don't work well because you have to do all of this either linear searching or binary searching. But for secondary storage, it's a different matter. We're willing to burn CPU cycles even doing a linear search here because a linear search takes far less time than even one block read. So we're willing to burn CPU instructions in order to minimize the number of disk accesses. So we're willing to go to bigger branch factors. So this does not work well in main memory. That's why we use binary search trees in main memory. But for secondary storage, the emphasis goes from speed to storage and minimizing disk accesses. Okay, so in this course, we're going to use, there's a difference between a B tree and a B plus tree. So a B plus tree stores only keys at interior nodes. And it stores records at the leaves, at leaves only. That's different than a B tree. A B tree will store records in the interior nodes as well, which cuts down on the branching factor, because let's say that you have, again, 4,096 bytes. Let's say that the keys are 4 bytes, but the records are 100 bytes. Okay, right away you can see if it was keys only, you could fit about 1,000 keys into a block, but you can only fit about 40 records. So you want to avoid putting records into the interior keys because they're going to lower your branching factor, the number of children you can put into a tree, or into a tree. So then you often hear, so there's some characteristics of of B plus trees. So with a B plus tree, you'll often hear us say a B plus tree of order M. Okay, that is the maximum number of children. So M is the max number of children. Which means, so there's several things. One, you have every interior node has up to m-1 keys. Because you can, if you think about it, if you have 3 entries, 3 keys, you actually, like 10, 30, 40, you actually can have one thing that's less than 10, the next one is between 10 to 30, the next one is 30 to 40, and the last one is greater than 40. So with m-1 keys, you can actually have m children like that. So every interior node has up to m-1 keys. The next thing is that every interior node but the root has at least the ceiling function of m divided by 2 children. So that means the implication is every interior node is at least half full. That's very important. So it's a requirement. The root is allowed to have as few as 2 children. So the root is the only exception. The root can have as few as 2 children. So every node but the root has at least m divided by 2 upper bound. The root may have as few as 2 children. So that's the restrictions on the interior nodes. So we're basically making sure they're at least half full. We put the same restriction on the leaves. Okay, so the leaves, so 4, okay, let L equal the max number of records that fit in a block, because that is what we will use. So we always try to maximize the number of records per block, because obviously when we do a read, we're getting that block for free, so we might as well maximize what we get. And what that means is our restriction there is that every leaf must have at least upper bound L divided by 2. So that's the ceiling function records. So again, the implication being every leaf is at least half full. The reason we do all that is that if all those restrictions are met, then the number of levels, so if all restrictions are met, the max number of levels is log upper bound m divided by 2 of n. So that's supposed to be the ceiling. I didn't do a very good job. Let's make the eraser smaller. Get rid. So these were supposed to be the ceiling. So if we don't enforce the fact, and this is supposed to be an m, let's make that clearer too. So that was supposed to be m divided by 2. So by forcing every interior node to be at least half full and every leaf node to be at least half full, we get that as our worst case performance. And that directly corresponds, we only do one read at each level, so that implies that the number of reads equals log m over 2 of n plus 1. Okay, this again was supposed to be, I'm doing a bad, supposed to be a upper, supposed to be a ceiling. Okay, the plus 1, this plus 1 is the read of the leaf. So that's reading the leaf. So even when you get to the bottom of the last interior node, you still have to do one read for the leaf. Okay? So we are out of time for today, but on Tuesday, there's no class Thursday because of fall break, and I'm not holding office hours on Thursday, so I will not be here. We'll take this up on Tuesday, and we'll look at the insertion and making it a full B plus tree. We'll also look at deletions on Tuesday, and then we'll also look at extendable hashing.